Yes. Okay, welcome to the live session. I'm Pandurangan. I hope you recognize me without the long hair and the thick beard. I'm the same instructor, except that I have just undergone a haircut. Okay, so
Mic. Yes, camera.
that's the mic. All right.
Camera.
So we have some questions. If you people have who are live have questions, I can directly answer you and then go for the static questions which have been raised already. I want to answer them, but before that, it's good to talk to the people who are online first and then go to the questions for which I have to. There are queries, about half a dozen queries are there, which I will answer and clarify. Okay. Anyone who is online have any queries? Any queries? Okay. Okay. So if you do not have queries, let me start answering the questions that have been raised. Okay. The first question is, can you explain the meaning and procedure for calculating alpha 2 SE, delta 3 SE, and so on? Alpha, alpha 3, alpha 3, what is the notation? That's it. Alpha 3 SE. So what is the meaning of this? Let's first see what this means. So S is a vertex in a graph, and there are several things, and E is another vertex in the graph. Alpha 3E means the minimum weight walk with at most 3 edges. Okay, alpha 3 means walk. So here is a walk of length 1, 2, 3. Okay, and this is 4. If this is yes, 1, 2, 3, 4. This is a walk of length 4. Let's label it as A, B. So yes to A, to B, to S, to E. This has 4 edges. Therefore, this is, and since the vertex is repeated, this is a walk. This is a walk. This is not a path. It goes from S to E, but S is visited again. Therefore, this is a walk. Fresh one. Next, I need more space to explain with an example. How do you go to the another fresh? It doesn't automatically scroll up and down.
Mhm.
Okay.
It's just a whiteboard.
Okay, yeah, we take one more.
One more.
All right. We will take a fresh one. Okay. So let me draw some example to. all these things. Let's say E, suppose the weights are like this, 1, -2, 3, 4, -1, -2, 1, 2, 6, 3, 2. Now, if you are considering walks or paths, it doesn't matter. This is the maximum alpha, let us say alpha 5 SE. How do I calculate alpha 5 SE? I consider all walks with less than or equal to 5 edges. This walk has got less than or equal to 5 edges. Okay, this one. It has got only 3 edges. So I have to consider the weight of that walk. 6 plus 3 plus 2, that is 11. And this also has got less than 5 edges. I have to add -1, -2, +1, +2, -1, -2, +1, +2, 0. So this is this walk. The other one, 1, 2, 3, 4, that also I should consider because at most 5. So when I consider that, it is 1, -2, +3, +4, that is 7, -2, 5, +1, 6. So I have considered all the walks which has got less than or equal to 5 edges. Take the minimum, and that is 0 here between 11, 0 and 6. 0 is the minimum. Therefore, in this figure, alpha 5 SE is 0. Now let us calculate alpha 3 SE. Alpha 3. We have to consider walks with maximum 3 edges. Therefore, I consider 6 plus 3 plus 2, this is 11. There are other walks in the graph, but they have more than 3 edges. I should not consider them. Okay, maximum 3 edges. Whatever the walk that have 3 edges or less, I should consider. Therefore, other thing I will ignore. There is only one. The minimum is this. Therefore, this is 11. Alpha 3 SE is alpha 2 SE. What is alpha 2 SE? Alpha 2 SE is maximum 2 edges. From S to E, you can have 1 edge or 2 edge walks. There is none here. There is no path. When there is no path, we have a convention that we would set that as infinity. Okay. Therefore, this is going to be set to infinity. Alpha, that is because there is no path. If there is no path of weight, no path consisting of edges 2 or less, right? There is no such path. Therefore, that is infinity. If there are several paths, you consider them and take the minimum, right? That is the definition of alpha. Next page, please. Yeah. No, I'll see whether I can do it myself.
New one. Right.
What is delta? Delta walk. Delta means path. This you remember. So you should consider only paths with number of edges bound by that number. So delta 4 SE means paths with number of edges less than or equal to 4 from S to E. You have to consider S to E. 4 means, therefore, a path of this kind is okay. It has got 2 edges. It is less than or equal to 4. I can consider this path. And S to E, if there is a path like that, that also I can consider. number of edges should be less than or equal to 4. All paths with number of edges less than or equal to 4, I can consider. So I can consider this, I can consider this. I should consider all these things for calculating delta for SE. So this is how, given a figure, given a graph and a picture, you find the walks and paths, find out how many edges are there, okay, and use that bound and solve it. So I hope this clarifies the definition of alpha and delta. If you have any questions, feel free to ask me.
Good afternoon, sir.
Yes, there is a question. Please go ahead.
Sir, with all due respect, for you teaching us this, I appreciate it, but this should have been taught in week 2, because week 2 assignment is already over and we were not sure how to do it, and none of the videos had this information.
Yes, I agree. There seemed to be some. See, what happened was we have planned the lectures and partitioned the coverage. Looks like this coverage has gone to the other week. But according to our earlier plan, this should have come to second week. So we set this question in the second week part. Now, what happened was this part has moved a bit, and that has caused a little bit of confusion. So let's see. But this definition is available even in other sources and books, which perhaps we might not have seen. Then that's okay. We will see what can be done with this. Okay. One thing what we can do is, like the typos and other things we can withdraw that question and add the question later. Right? So if that looks like a fair decision, what I would do is I will move these questions, or one or two questions I will ask again in another week after the coverage, so that you will get the credits for it. I'll make sure that these questions are put in a quiz which is after the topics are covered. But what you have pointed out is correct. There was a minor change in the plan, but the questions seem to have got jammed up a bit. We will rectify it. Okay, I assure you, I would do that for you.
But what about the week 2 marks?
I have to check with the administration on that, and we will work out that detail. For example, if the question is withdrawn, then from that week, for example, if I withdraw question, 3 questions, if I withdraw, then in that week, I will have only 7 marks. If I move these to another one, that will have 13 marks. But total marks will come to whatever was planned. Only thing is, you will not lose the mark, and I will discuss with the administration as to how it can be done. Okay, I have to talk to the people. This is the first time that I'm offering that. I'm also messing up a bit in this kind of alignment. It was almost like that. There was some mistake that has happened. My apologies for this, and I will set it right in discussion with the administration here. Okay.
Sure, sir. Thank you very much.
We will talk to the admin and we'll
sir.
No, next question.
Next question is log n factorial.
Sir,
Question.
good afternoon.
Good afternoon. Tell me, please.
Sir, thank you. And I only posted that question, right, which you have answered just now. The thing is, almost the 8 questions are from this one, sir, in your assignment too.
Okay.
Out of 10. But even I have tried it in other sources, but I was unable to find the procedure.
Actually, there is no procedure for it. You have to look into the picture and hand calculate the details, because algorithmically, if we try to
now
do
it is okay, sir. You have explained it. Now it's okay. You have explained it. It's clear. Even your lectures were very clear. Like
Oh,
you are
thank you very
explaining
much.
everything in a nice manner. And even this, the other one I have not posted, but the one what you have started, I think. For the assignment to one, I gave the answer as log n, but in the key it is given ln n as the answer for one of the
I mean, both,
problem.
see, technically speaking, for the
Uh,
log, base doesn't matter, whether it is base
But
2 or
the
base
base
10.
usually if in as a mathematical thing for log we are using e as the base, sir. Maybe in
No, no, no,
calculator.
not E is used for ln. That is called
That's what.
natural logarithm.
Yeah,
So,
natural log.
can you give me the screen? 1 second. I'll write down the. See, ln is natural logarithm.
That's what. That
That is
is a
why this
log base
n
e,
is there.
right?
Therefore, for this, the base will be e. For
yeah.
all other things, it will be log to the base 10, log to the base 2. For all these things, we use the term log.
No,
For
sir. That is
natural log, we
okay.
use
But
ln.
usually in max, I am telling, right? Even for differentiation, also we are writing log x. For
Yes.
natural log. For natural log only, we are writing log x. We are
Okay.
not using that ln of
Yeah,
x.
yeah. And
Yeah.
see, in computer science, we do not want to really distinguish. Even in maths, what happens is some books will use ln, some books will
ln.
use
Some books will
log.
use log. That's what I am telling. But
Therefore, I
in the
accept both answers. Whether you
but it is
use
given
log.
as wrong. That's what
Huh?
in the assignment one.
No, we have corrected it.
It is being.
No, sir, it's given wrong.
Hello, one
It's
second.
given a wrong, sir.
Excuse me.
Yes.
It is being corrected, and you will be given the notification in few days. Okay.
Okay.
Wait for the one more notification announcement. Okay.
Yeah, because what we have already instructed or informed the administration is ln, log, both are acceptable. Please award marks for, because some people will write log, some people will write ln. It's all same. Because in Big O, it really doesn't matter what the base is. By base changing rule, they change by only a constant, which is okay in Big O. Therefore, it really doesn't matter which one you use, all will be awarded full marks. If there is a mark cut, that will be corrected and rectified. And as Madam said, the notification you will receive soon. If there is any query or question, please contact us and we will sort it out. No problem.
Okay. Thank you, sir.
Yes. The correct answer should never be punished with wrong judgment. So we will ensure that.
If it was like filling the blank. If it was like choosing, we know that one, right? Which one to
I know.
choose.
Yes. Yeah. In fact, even for me, had I given that as a multiple option question, people would have done correctly. And okay.
Okay, sir, thank you.
So,
if you don't mind, could you just explain the second one in assignment 1, the second question?
Second question in assignment 1. What is the second question in assignment 1?
Which is the correct one? There are 4 options.
What are the options given?
2 to the power n equal to theta n square.
2 to the power n equal to theta n square.
2 to the power n equal to omega n square.
Equal to omega n square.
2 to the power n equal to omega n to the power 10,000.
N to the power 10,000. Omega.
It's a big O, sir.
Okay.
It's
Big O. Sorry.
Yeah.
Sorry, my confusion.
No problem. Big O and
2 to the power theta. Sorry, 2 equal to theta 2 to the power n minus 1.
2 to the power n minus 1. Which one is correct? Was the question, right? The answer is 2 to the power n equal to theta 2 to the power n minus 1. That is because you can see that 2 to the power n is less than, let us say, 4 times 2 to the power n minus 1. Okay. 2 to the power n is greater than 1 times 2 to the power n minus 1. So you have constant 1 and 4 fitting that definition. What is the definition? F of n is of theta g of n if c times f of n less than or equal to G of n is less than or equal to C2 times f of n for some constant C1 and C2. We have 1 and 4 acting for C1 and C2 here. Therefore, they are of the same order, which means this is the correct answer. What happened was there was a typo in this 000 has slipped down, and some mess has happened while mounting that the question paper, or I don't know what has happened. There was some mess around. I think that's the reason why we withdrew that question or something like that. Okay. Okay. This question is withdrawn. So whether you have done it correctly or wrongly, don't worry about it, because there was a typo here. This question is withdrawn. That is for the academic marks are concerned with. But as far as our technical answer is concerned with, this is the technically correct answer.
Sure, sir. Thank you.
Okay. Now, log n, that is also answered. I have a question. What is we can never have a cycle in the path. Yeah, there is no path cannot contain any cycle. Okay. We can never have a cycle. Even the graph contain a cycle which have positive. Yeah. Whether weight is positive or not, path is something like this. Right? It is a sequence of edges. That's all is path. No repetition. So a walk may contain a cycle, because in a walk there can be a repetition. So you can start from here, go like this, and come back and go on. So a walk may contain cycles, but paths cannot contain any cycle, because in a path, no repetition of vertices or edges. That is the major difference. Okay, now there is one question on what is the significance of negative weights. Okay, why we should consider negative weights. See, what happens is you have, for any concept, if it is a positive, there is something called a negative. Okay, opposite of it. If there is a profit, there will be a loss. For example, if I am, for some people, going in one way could be beneficial, but going in the other way could be a loss. In that case, we want to model that with some numbers represented in a positive way and some numbers represented using a negative numbers. And there are other applications in which what we do is we take logarithm to the weights. When you take log for the weights, you get negative numbers, right? If you take log to the base 2 of a number that is smaller than 1, then you get a negative numbers and so on. So it all depends on the application, but rest assured that there are applications which will require the treatment of negative numbers also. And that is the main reason why in a weighted directed graph, we allow all possibilities: positive weight, negative weight, zero, even absolutely zero weight is also allowed. Okay. So it is all there in applications, except that those applications we will not be able to discuss in detail now, but they are there. Okay. So
Please post any more questions here. Either you can unmute yourself and talk, or
type.
Type it out. Either on, even if somebody is on YouTube, they can also type here on YouTube.
I don't know whether they can do that in YouTube.
Mhm.
Or top chat. Okay. In general, are you able to follow my lectures and without much difficulty? Are you able to follow the flow? If you have any such difficulty or something like that, please raise the question or seek the clarification. I'll be very happy to come back and then discuss them. In another 15 days, maybe we can say that right now. The Monday after, what date that would be?
26th.
26th. The Monday of 26th, we shall meet again like this, so that you would we can discuss. All right. Any questions that you may have, I will clarify. And if additional examples are to be worked out to illustrate the points that are discussed but not fully clarified, we can. This question is done. Let me see if there any other question that is. Yeah. So Sagar is here, right? Sagar Ludia is here. Pattern the end semester, all end semester exams, they have the same pattern which is recommended, right? If you look into the NPTEL site, for example, there will be some questions that are asked in the quizzes and midterm and take-home assignment. Some questions from that you will get in the final exam. Certain questions will be modification and change of those things. And then the area, the coverage. For 8 weeks, we have given you 8 assignments. From each topic, you will have one small questions and other things. You have both multiple choice questions, fill in the blank questions, all kinds will be there. But it will be very similar to what you have already experienced. When you have solved the problem in assignment and quizzes, it's the same for the final exam. Everything that you have seen is a good model for.
Hello, sir. Good afternoon.
Yes, good afternoon.
I'm audible clearly?
Yeah, I'm able to hear you. Go ahead.
Okay. Sir, I'm a third year computer science student. I'm just taking this class, and your explanation is very good, sir. I can understand each topic. Thank
Okay.
you, sir.
Welcome.
And I just wanted to ask that we have learned in the second week the shortest path algorithm, and the third week the Bellman-Ford. Can you able to draw a new example, a real life example, where if we have to build a software from the scratch, then how we can apply that knowledge? Maybe you can take one simple example.
Look, the real life examples and the whole software package will be complex. But if you look at the Google map and the way in which you are navigated, okay, these are all solving the shortest path problem. The real world. You are using you're quite using the Google map, right? For going from one place to another
Yes,
place.
sir.
The Google
Definitely.
map is nothing but the shortest path algorithms and other things are what is used. It has got the complete city map. It has got the distance and other things, and it can even estimate how much time you will take to go from one place to another place by car,
Yes.
by cycle, by walk, by train,
Yes.
because they have all those data. So you have a lot of such real world applications are there for shortest path problems. And there are other problems that are not even connected with this kind of a network that can be modeled as a shortest path problems. Therefore, solving the shortest path problem is it's such an enrichment. I can give you one. I can suggest a recommendation. I'll give you a reference.
Yes.
1 second.
Even Google Maps nowadays shows that how much congested the area is, the red light and also.
Yeah, of course, quite a bit of all these things
Yeah.
are used.
Yes, yes.
So there is a book by Eva Tardash, okay, on algorithms. It's a book. There you can see a lot of applications of shortest paths, various problems that can be solved using shortest path. This book is available in Indian print. There is another book probably you have to get only in library, that is Ahuja. Ahuja, that book on network flows. This is a very good book. It's an award-winning book for operations research, and there are other authors also. There are 3 authors. I have given only Ahuja. You can Google search Ahuja's book on network flows. This has got large number of examples of real-world applications that can be solved using shortest path problems. Real-world applications, full details. They are all discussed in this Ahuja's book. Ahuja's book on network flow is a very good reading, enrichment reading. You will enjoy reading it. If you are looking for real world applications, you should access Ahuja's book. Very friendly to read, very easy to read.
Okay.
With the kind of discussion we have in the class, this is good enough. You can go to Ahuja's book, go to the chapter on shortest path. You can start reading that. Absolutely no problem. And you can see the
Okay, sir.
applications also there.
Thank you, sir.
Welcome.
Thank you.
Okay.
Hello, sir.
Yes, please. Who is that?
Sir, Sagar speaking.
Oh, Sagar. Go ahead, Sagar.
Sir, can you please explain what is the relationship between the lower bound, upper bound, and these notations that we have, theta, omega, and
Yeah, sure,
big
sure.
one?
See, what we want to do when we want to compare 2 different algorithms is how efficient they are. So I have an algorithm A1 and its running time is, let us say, n square. And I have another algorithm A2 that has got n log n. Now it won't be plain n square and n log n like this. It may be like 7n square plus 3n plus 9 kind of a thing. And this n log n also 6n log n minus 2n plus 3 kind of a complexity. This will be the complexity. Now, how do you compare? Okay, when you want to compare 2, which one is smaller, which one is bigger, you have to say, right? So for large n, which one will be smaller, which one will be bigger? Now, if you look at 7n square for large n, this will be way larger than 6 log n. As n becomes larger and larger, this is going to become very large. This will also become large. This will also become large, but that is becoming larger at a rapid rate. That is called the growth rate. Growth rate is how fast it becomes bigger. As n becomes larger and larger, how big f of n becomes. Different functions will become bigger at different rate. Okay. So what we are going to do is that we are going to compare the growth rate. So if f of n is big O of g of n, then growth rate of f of n is less than or equal to growth rate of g of n. If f of n equal to theta g of n, then growth rate of f of n is equal to growth rate of G of n. They have the same growth rate. They grow at the same pace. As n becomes larger and larger, you can see that the way in which 7n square plus 3n plus 9 and 4n square minus 6, both of them will grow in a similar fashion. They all grow like n square, right? That is the reason why we determine the growth rate. If some function has got higher growth rate than another one, we prefer the one with lower growth rate. So, for example, n log n is big O of n square. Its growth rate is equal or larger. In this case, it is strictly larger. Therefore, I would prefer this. How to find out which one has got a higher growth rate or which one has a lower growth rate? You consider f of n by g of n. You let n go to infinity. Because as n becomes larger and larger is modeled by n going to infinity. If n going to infinity, if this going to 0, what does that mean? Denominator is becoming larger and larger more rapidly than numerator. Numerator is also becoming larger, but that is becoming larger slowly. Denominator is becoming larger rapidly. So what happens is the ratio becomes smaller and smaller. So if you consider n log n by n square, this goes to 0 as n goes to infinity. Very simple calculus or any mechanism you can use. That means n log n has a smaller growth rate. N square has higher growth rate. So between n log n and n square, I would prefer n log n. This kind of conclusion I am able to get by comparing complexity functions. So the purpose of big O, theta, all of them is compare two functions. Complexity function. In computer science, we are interested only in comparing the complexity functions and choose the function that has got the slowest growth rate, minimum growth rate. It becomes larger, but slowly. That is the objective. In order to judge which one has higher growth rate, which one has slower growth rate, we use the theta and big O. That's all. It's just a mathematical way of saying they have the same growth rate. One has a higher growth rate. These two things are said using a notation. Have I answered your question? Is it clear now?
Yes, sir. Yes. Sir, one follow-up question on that.
Yeah.
For example, I have an algorithm which is going to take order of n square of time, right?
Yeah.
Can I state that in any situation, whatever input I take, in worst case, it is going to take order of n square only. It will not go beyond that.
Yeah, it won't go beyond that at all. That is the maximum because worst case complexity means upper bound. That's a maximum. Therefore, nothing can exceed that.
Right.
No inputs cost complexity will exceed that.
And similarly, let's say we have an algorithm which is having omega of, let's say, n.
Yeah.
So which means that then algorithm is going to take at least of n amount of time.
Yes, that's right.
So we can we say that the omega is the lower bound of an algorithm and the big O is an upper bound of an algorithm?
Yes, omega is a lower bound, big O is an upper bound. You are right. Absolutely right.
Okay, sir. Okay. Thank you so much, sir.
Okay. Thank you very much.
And sir, one more question.
Sure. Go ahead.
Dijkstra's algorithm and Bellman-Ford algorithm.
Huh.
So in Dijkstra's algorithm, if we have a negative weights.
Yeah.
Say a graph which doesn't contain a negative cycle, but it has a negative weights.
Okay.
So can a Dijkstra algorithm produce a correct output?
No. Even if one negative edge is there in the graph, forget cycle, everything. Even if one negative edge is there in the graph, Dijkstra's algorithm is not guaranteed to work. Dijkstra's algorithm requires that monotonicity. That is, I must be able to find out longer and longer. Suddenly, certain thing becoming smaller and again becoming large. Dijkstra's algorithm cannot handle that. So Dijkstra's algorithm will go wrong even if one negative edge is there in the graph. Therefore, it should not be applied. Dijkstra's algorithm should be used only if you have a graph in which all edge weights are positive. That is a condition. That's a property and no compromise on that. Whereas Bellman and Ford, your input graph can have mix, positive weight, negative weight, zero weight, anything it can have. As long as there is no negative cycle, that graph can be processed by Bellman and Ford and it will give you the clean answer.
Okay, so sir, actually I have the confusion in that statement only. For example, can we say that the Dijkstra's algorithm may or may not give a correct result when we have a negative weight?
Yes.
Or we can say that it is always gives a correct result when we have, or let's say I have two statement. Dijkstra's algorithm will give always correct results when we have positive weights. That is right.
Yes, that is right. That statement is clear. That is mathematically proved and so on.
And when we have negative weights, Dijkstra's algorithm will give always wrong. Is it right or wrong?
No, no, no. It may not give always wrong. See, what happens is, if that negative weight is not reducing the costly path by a big value, right? In that case, even if there is a negative weight, its effect might not be felt during the execution. Although it's a kind of a double wrong. I would have ignored it. I might not have considered that at all, because once a vertex is moved to S, I'm not revisiting that. To that vertex, there might be a negative edge, which is supplying a shorter path, but that is all ignored, right? So I am ignoring certain edges. If the ignored edges are negative edges, it may cause problem. If the ignored edges are non-negative, it may not cause problem, but we cannot say beforehand. Before running a Dijkstra's algorithm, we can't say whether it will work or not. Therefore, all we can say is, if you run Dijkstra's algorithm on a graph that has got some negative weights, it may output some numbers, but you can't trust them. It may or may not be correct. That is the correct statement. You have given the correct statement. You can't say it will always give wrong answer. No. Sometimes it may give right answer. Only problem is that you have no idea of you knowing whether it is a right answer or a wrong answer. Sometimes it's a wrong answer, you will be able to detect, hey, here is a shortest path, but this algorithm is outputting that one, which is very bad, and all you will be able to see in toy example. But in big examples, we will not be able to see. That is the reason why we will never apply Dijkstra's algorithm, even if the graph has got one negative edge.
Thank you, sir. Thank you. And sir, one more question.
Yes.
Sir, in comparison of Dijkstra's and Bellman-Ford,
yeah,
do we have any example in such situation where we don't apply, apart from the negative weights, we don't apply Dijkstra, but we have to apply the Bellman-Ford algorithm? Is it, I mean, any kind of?
Yeah, no. If the graph has got no negative edges, right, don't apply Bellman and Ford. Bellman and Ford will take more time.
Right. It is going to take
because it is going to take NM.
Right.
Whereas you have in Dijkstra's algorithm, I can implement it in n log n plus m time. Therefore, if all edge weights are positive, there is no point in working on Bellman and Ford algorithm. That is inefficient for the graph that has got all positive weights. But if the graph has got a mix of positive and negative weights, Dijkstra's algorithm I can't use anyway. The only option I have is Bellman and Ford. I use Bellman and Ford and solve the problem.
Okay.
But if all edge weights are positive, I will work only with Dijkstra's algorithm. I will never touch Bellman and Ford for all positive weight graph.
Okay, so sir, the Bellman has implemented that algorithm only basis of the negative weights that we have, because we already have Dijkstra's algorithm, na? That is all.
No, yeah. I mean, see, I know that Dijkstra's algorithm cannot be used if the graph has got negative weight. There are applications in which I may have to use positive and negative weights. So if I want to solve the shortest problem on those graphs, what algorithm I have in my hand? The only algorithm, if it is a Dijkstra, I know that it doesn't work. So I have to discover a new algorithm, right? That is what was done. In order to deal with a graph that has got both positive and negative edges, Bellman and Ford has given you an algorithm. You apply it only if the graph has got mixed edges. If the graph has got only positive edges, don't use that. Of course, if you use that, you get an answer. But the only thing is that is inefficient. For a graph that has got only positive edges, we have Dijkstra's algorithm that is very efficient. So let us use that. We have option for positive edge weights. You can run Bellman and Ford, you can run Dijkstra. You use Dijkstra because it is efficient. If a graph has got positive and negative weight mix, you have no option. Only Bellman and Ford works. You have to just use it to solve the problem.
Yes, sir. Thank you so much, sir. Thank you.
Okay. Welcome. Let's meet again on 26th.